Hello YouTube, it's Roman. I am back and today I want to talk about Brownian motion. Brownian motion is a fundamental concept of quantitative finance, of stochastic differential equations, stochastic calculus, and there's some key properties of it that make Brownian motion what it is. And what I wanted to do was accompany this introduction in terms of the three key properties of Brownian motion with a Jupyter notebook to better explain some of the results that we've seen in past videos and better explain integration with respect to Brownian motion as well. So for starters, let's take a look at these properties of Brownian motion. So consider a starting point, or t is an element of some time interval t0 to cap t. Now, when I say this time interval, if you want to make it more concrete and you want to make it real, I know a lot of quantitative finance, a lot of financial mathematics makes things general, and that's kind of very nice and good. But I want to make sure that we have concrete examples to illustrate what we're talking about. So think of this time interval as 5 days. Okay, on an x-axis. So it's two-dimensional. We have an x-axis. Time zero is zero. It's today. Then 1, 2, 3, 4, 5. Think of a discrete step in time as one day, and we have this closed interval of time on the x-axis. Now, at each step in time, so each day, we are going to match that day with a realization of Brownian motion, meaning the y-axis is going to be a process. It's going to be this Brownian motion. So we'll have a point here on day zero, move to the next day, that point may be here, move to the next day, that point may be here. And over the course of 5 days, we're going to have time on the x-axis and then 5 points in a two-dimensional space. Okay, so what's the first property of Brownian motion? Well, the first property is that W, meaning the process, Brownian motion, at time zero, so we could think of that as zero, which is today, is equivalent to zero. More formally, that the probability of the Brownian motion at time zero is equivalent to zero is equal to one. There is a difference in saying that the probability of something is equal to one and certainty in an outcome. That those are two different things. Very similar to a limit in calculus, how the limit at infinity is, say it converges, it would be perhaps to a value such as one. It's similar in notion. It's not one, but it's the limit as it converges, or the limit at infinity it converges. So it's a similar notion. Try not to get too hung up on it, but we have this first property that the Brownian motion at t0 is equal to zero. Okay, great. So the next property, property number two, so this is property number one right here. And then property number two is going to be this. It's going to be that Brownian motion is almost surely continuous, or that the probability limit as n approaches infinity of the process, so Brownian motion, is equal to the Brownian motion, which is equal to 1. So again, this is built around the notion of the probability that something is equal to 1 is not the same as certainty in an outcome. Again, try not to get super caught up on the mathematics of this definition of these properties. You can just think of it as almost surely continuous. And if you really want to dive into the nitty gritty, then you can formalize the definition of what almost surely continuous is by going on math stack exchange or something. But lastly, that the Brownian motion has independent and stationary increments. Now, this is a very important property. What are we saying when we say that the Brownian motion has independent and stationary increments? Well, we're saying that the Brownian motion today, so we're at time zero, we have time on the x-axis. Time zero, Brownian motion today, and the Brownian motion tomorrow are going to be completely independent of one another. And more formally, we can realize this difference in a distribution. And it's a normal distribution with a variance of the step in time. So you'll notice if we take the difference of Brownian motion at t plus 1 and t, and we take that difference, it's going to be distributed normally with a variance of t plus 1 minus t. So it's going to be that time step. It's going to be the step in time is the variance. And if you watched any of my previous videos, you'll notice that we generate the Brownian motion, the increment, we generate it by a normal distribution with the standard deviation of the square root of the step in time. So this is exactly what we're saying. We're actually using this property of Brownian motion to simulate that path, simulate that process, as we've done in the arithmetic Brownian motion video and the geometric Brownian motion video. So this is where that's coming from. This is coming from the property of Brownian motion, the independent stationary increments, the third property here. Now, these properties are formally outlined in this book that I have referenced before, Mathematical Modeling and Computation in Finance. It's a tremendous book, so I want to ensure that I'm making the reference to this book for these properties. And if you're interested in this sort of thing in the quant finance space, phenomenal book, phenomenal book. Definitely check it out. Not the first time that I've referred to it for my own sake or for these videos, so definitely check it out. Now that we've built the mathematical foundation of Brownian motion, what I want to do is I want to talk about it in Python to make it, more intuitive, to make it very easy to interpret. So for starters, for visualization, I'm going to import matplotlib, that plyplot as PIT, import numpy as NP. So we're going to use matplotlib for visualization and numpy for generation of the Brownian motion. So let's start by generating Brownian motion. Okay, so to generate Brownian motions, let's create that time interval that we referred to. So we have 0, 1, 2, 3, 4, 5. So these are just 5 separate days. 0 is now, 1 is tomorrow, 2 is 2 days from now. You get the picture. So that's going to be our x-axis, okay? We're operating in 2 dimensions where the y-axis represents the outcome of our stochastic process of our process Brownian motion. So how can we create Brownian motions in Python? Well, it's actually very easy. So W is going to be equal to our Brownian motions across this 5-day period. And what we have here is W of T0, W of 0 today is equal to 0. So we're going to start at 0. And then at every step, we're going to realize a new Brownian motion. We're going to essentially draw from a standard normal distribution, and we are going to say that is our realization of Brownian motion for that day. So to do that, we can do for I in range of the length of time minus 1, because we already added 0 to the list. We are going to append np.random.normal 0, 1. So if we do this, and then we do plt.plot T and W, we'll actually get Brownian motion. So this is going to be Brownian motion. It's a realization of Brownian motion over the 5-day interval. And we can, simulate this as many times as we'd like to get different values. But we have a couple of key properties that are being displayed here. And for one, it's that the increments are independent and stationary. And to better visualize this, what we can kind of consider is the distribution of outcomes on each day. So what I'm saying is this value at 0 is always going to be 0, right? W of 0 is equal to 0. That's a property of Brownian motion. But at 1, we're drawing from a standard normal distribution. At 2, we're drawing from a standard normal distribution. At 3, at 4, at 5, we're drawing from a standard normal distribution. So what we should see is if we drew 1,000 points, the points should look like they're distributed standard normally. So if you drew a vertical bell curve, it would fit the distribution of Brownian motions very, very well. So I got a picture of the standard normal distribution here. You can see that at the tails, we have -3 and 3. It starts to tail off at around 3 and 4, as you can see here, for a standard normal distribution. So let's go ahead and try to actually realize this. So what we can do is we can say, we're going to draw how many paths of Brownian motion. So essentially, how many realizations across this 5-day interval per day do we want to have? So let's just say we're going to do 1,000. And we'll say for j in range n, so we'll have 1,000. We are going to have a paths list to store all of the paths. We're going to reset the Brownian motions array, and we're going to say for I in range less than, So for I in range, the length of the time minus one, because we have this already, we're going to append a realization, and then we can just append that to the paths. And then we're going to reset, we're going to do that, we're going to do that. Okay, cool. So now we have a set of realizations. So path 0, this is one outcome. So actually what we can do is we can just plot each path, this path 0. So for example, this is one outcome of Brownian motion across the 5-day interval. This is another outcome. This is another outcome. And so on and so forth until you have your thousandth outcome. Okay, cool. So we have a collection of outcomes of this Brownian motion. So how can we visualize the standard normal distribution at each point in time? Well, it's very easy. We can just create a loop to plot each point, and then hopefully the limits of the y-axis will be 3 and -3. That's, exactly what we would hope for, unless we're not generating the Brownian motions correctly. So let's give this a shot. So for path in paths, plt.scatter, we're going to create a scatter plot of the path um, for all of the points in that collection of points. And we should get, yep, hey, check this out. This is pretty cool. So we can see that the density of points, so obviously at 0, we have 0, just as the property of Brownian motion says. But at 1, it's starting to look like a standard normal distribution. We go from 3 to -3, and the density of points, you can see, I'll zoom in so you can see, the density of points is heavily concentrated around the center, mean 0, just like a standard normal distribution. And towards the end, you start to get these outliers, just as you would in a standard normal distribution. So we can see that we're effectively generating the Brownian motions correctly. Okay, well, that's pretty cool. But what I also want to talk about and address in this video is the integral from the analytical solution to geometric Brownian motion. So how do we integrate with respect to geometric Brownian motion, and what are we actually doing? Well, let's just start by looking at the math. So if we look at the math, right, we have, let's use some LaTeX, the integral from t0 to cap t. This is from the geometric Brownian motion video, so if you haven't seen this before, check it out. Otherwise, just follow along and see how we can solve an integral with respect to Brownian motion. dwt. Okay. So we have this integral with respect to Brownian motion over time. Well, we solved this integral in the video for geometric Brownian motion, the analytical solution to the stochastic differential equation. So we know that it's going to be sigma w cap t less w t0, which is just equal to sigma wt, because we know that wt0 is equal to w0, which is just 0, right? So we know what this is, right? We solved for this, and I kind of just took this as a given in that video, which is why I wanted to make this on Brownian motion and talk about the implications of this integral here. So what are we doing when we actually integrate, right? What are we looking for? Well, we're looking for the area under a curve in a sense, but we're also trying to account for the change, right? The cumulative change over time. That's really what the integral is. When we take a derivative, we're looking at the change, right? And when we're integrating, we're going backwards. So you can really think of it as trying to sum up the change over time. But we know that each point is independent and stationary. So do we really need to consider every point to find the change over time? No, right? We really only need to consider the start and the end. Hence, when we're looking at this integral from t0 to cap t, or 0 if you would prefer, we're really only considering day 0 and day 5 to try to find the cumulative change. If this was P&L, right, like trading P&L, it would be exactly the same because you don't really care what your P&L was yesterday. Your P&L is the accumulation of your portfolio up until now. So if you knew your P&L, you were net zero at say 5 days ago. So say we're here, we were net zero, but now we're up here, then you would just take that difference to find the change over time, right? So if we look at this path 999, and we wanted to compute the integral with respect to Brownian motion from t0 to cap t, then all we need to do is look at the Brownian motion at time step 5 and subtract it from the Brownian motion at time step 0. Well, we know time step 0 is going to be 0, so trivially, we know that the integral is just going to be the Brownian motion at the terminal step. So if we were to try to compute this value, then we could if we had one realization of a sample path, which we do. So if we were to look at this, right, is this is one realization of Brownian motion. So if we wanted to find this integral of this realization, then all we have to do is find the endpoint of the Brownian motion. So what we would do is simply say, okay, we have this path 9999, and we want the latest realization of Brownian motion is 0.73791. You get the picture. So that's this value right here on day 5. And if you notice, disregarding the rest of the points, we started at 0. So if we wanted to find this integral over time, now you could disregard sigma, just consider sigma as a constant. Consider sigma as just 1, right? In the context of geometric Brownian motion and a set of outcomes, this changes. But consider we have one realization, okay? We can see very clearly that the cumulative change in Brownian motion over time is just the latest innovation in Brownian motion. And that's exactly what we see here, right? It doesn't matter what this one is, doesn't matter what this one is, doesn't matter what this one is. They're independent of each other. They're completely independent, they're stationary increments. That's the point of Brownian motion. When you look at a geometric Brownian motion, when you look at an arithmetic Brownian motion, this changes because you have they're not independent. They're not independent. It's just the way that process functions as a stock process. That's the point of the process itself, is to try to capture the empirical data that we see in returns, right? So we know that returns are not necessarily perfectly log normally distributed, but that's exactly what GBM tries to capture, right? And we have other settings to use arithmetic Brownian motion, and so on and so forth. But this is exactly what we're talking about when we're talking about an integral with respect to Brownian motion over time. So you can even disregard the sigma. So if I was to rewrite this integral, right, from 0 to t, actually forget it. Let's just talk about 0 to 5. Right? If this was a quiz and I was like a teacher or something, then if we wanted to do this, 0 to 5, the change in Brownian motion, right? We're integrating with respect to the change in Brownian motion, then that's going to be equal to the Brownian motion at 5 less the Brownian motion at 0. And we know that that's just going to be the Brownian motion at 5 because W of 0 is 0 by our properties of Brownian motion. And W of 5 is just going to be this value here. This is the realization. This is it. So if we find W of 5, we find the solution to this integral. And lo and behold, this is just getting the last item in the list. If it's better for you to see this, then if it's better for you to see that, for the fifth element in that path, which is the solution to this integral, then so be it. But it's the same thing as referencing the last element. So this is precisely what we're referring to when we're looking at the change in Brownian motion over time. So hopefully this was a clear and concrete example about Brownian motion. I know that it can be a very confusing topic when there's randomness induced cross-sectionally, especially as a time series when you're considering something like this. So it's like, it's a low dimensional problem space in the sense that you have two dimensions, time and a process, right? But when you first introduce to things like this and you're like, hold on, there's a distribution at each step in time, it kind of can be confusing. So hopefully this made it a little more clear looking at the distribution of points over time, and then solving some sort of integral with respect to the change in Brownian motion over time was a little more concrete. So So if you have any questions, feel free to drop them in the comments. I'm happy to listen to suggestions for future videos as well. But as always, thank you for watching, and I will see you in the next one.